Here we have question 3. An electrical heater consists of two heating elements, E1 and E2. The elements are connected in parallel. Each element has a switch and is connected to a supply of EMF 240 volts. The supply has negligible internal resistance. Element E1 is made from wire that has a cross-sectional area of 6.8 times 10 to the negative 8 meters squared. The resistivity of the wire at the operating temperature of the element is 1.1 times 10 to the negative 6 ohm meters. The total length of the wire is 4.5 meters. Show that the resistance of E1 is 73 ohms. So which formula are we going to use? Obviously this one over here, because we need to show the resistance. We've got the length, we've got the rho, the resistivity, and we've got the cross-sectional area. So it's just a matter of putting that in. So we get R is equal to 1.1 times 10 to the negative 6 times your L, which is 4.5 meters, divided by 6.8 times 10 to the negative 8 meters squared. It's quite important to always check that your units are the same. I mean, the units are all in meters here, so there's no problem. All of them, you've got meters there, meters, meters squared, so that's all fine. But sometimes you may have it in centimeters, millimeters, and you've got to be able to change those over. So let's just do that. So it's 1.1 exponent negative 6 times 4.5 divided by 6.8 exponent negative 8, and we get 72.794. so that is equal to, that's 72.79, which is equal to about 73 ohms. Let me make that an equal sign there. Okay, so going on to 2, calculate the power output of E1 with only this element connected to the supply. So here we have closed E1. We therefore are going to have a potential difference across E1 also of 240 volts because there is negligible internal resistance. So all the energy that is going to be lost is going to be there. So we're going to have that. The power, we would be using these set of formulas here depending on what we've got. We've got our V and we've got our R. We want to work out that. So we can use power is equal to V squared over R. So we're going to get 240 squared divided by our R, which is 73. So let's just do that. 240 squared divided by 73. And that gives me 789.04 watts. The number of significant figures here, we've got 2, so we're going to have 790 watts would be our answer. Then in 3, it says element E2 is made of wire of the same cross-section and material as E, so therefore the resistivity is the same. The length of the wire in E2 is 1.5 meters. Determine the total output when E1 and E2 are connected to the supply. So what we're going to have to work out firstly here is the resistance of E2. So if I just can work over here, the resistance of E2, we're going to be using that formula again. We're going to have the same resistivity, so that's 1.1 times 10 to the negative 6 times, but instead of 4.5 we now are at 1.5, and we're going to divide it by the same cross-sectional area, 6.8 times 10 to the negative 8. So I'm going to have that, let me just calculate that, 1.1 exponent negative 6 times 1.5 divided by 6.8 exponent negative 6, and you get I'm getting something wrong. I'm getting 0.24 here. Let me just do that again. So I'm getting, sorry, this should be negative 8 here. I think I did negative 6. So 1.1 exponent negative 6 times 1.5 divided by 6.8 exponent negative 8. And there we get 24.26. So I'm going to say it's about 24 ohm. Now, it's important. The answer that I got before was 0.24 ohm. Now, I straight away knew that that wasn't correct because the only thing I'm changing here is my length. Now, we didn't even need to really do this calculation because it would just be a proportional value. This is 1.5. This over here is 4.5. 4.5, so it's actually just going to be a third. 24 times 3, about 72, so you're going to have basically a third of that. So we've got that is 24 ohms. So basically we've got here, we got this is 24 ohms, we got this is 73 ohms. Now when they're both closed, we need to work out the combined resistance of both of them. So I'll do this over here, 1 over R total, 1 over 73 plus 1 over 74. When I find RT, it's just going to be the inverse of that. So I can just do that all on my calculator. Sorry, not 74, 24, 1 over 24, like that. And we're going to do the inverse. And that will give me my R total. So let's just do that. So we're going to have brackets. 73 inverse plus 24 inverse close bracket inverse, and I get a total of 18 ohms. So I've got 18 ohms as a combined resistance for both of them, 18 ohms, and therefore determine the total power. Total power will equal V squared over R. So it's going to be 240 divided by 18 now. So, and that's 240 squared divided by 18. So 240 squared divided by 18 into 3,000. We're going to get a total of 3,200 watts when you have them in parallel. Good, so let's go over the page because there's some more questions here. It says, with reference to the power output, explain why it would be inappropriate to connect the heating element in series. So what we've got here is that we have the power output of 3,200 watts. So that means that you are turning electrical energy into heat energy 3,200 joules per second, and that's obviously heating up whatever you're wanting to heat up, water or whatever. Now, if I put them in series, I would have something like this. I would have my 1, which was 73, plus my 24 ohms like that, and I would have it like that. Now the power output would equal again 240 squared, but you would actually divide by these two added together. So you would be dividing that by 97. So we'd have 240 squared divided by 97, and you'd get 594 watts. So you'd only be converting 594 joules per second. Therefore, you're not going to get much in the way of heating. Heating would be too low. Okay, so if you do that, if you show some calculations here, you'd need to do some calculations, put that into here, and you should get the marks for that. Now we're moving on to a section which is actually in Unit 6. But let's do it here. So it says over here, each element in the electric heater is wound as a coil as shown. Each turn of the coil may be considered to act as a current-carrying long straight wire. On the diagram, draw the magnetic field around a current-carrying long straight wire. The arrow shows the direction of the current. So this is your eye. Now, to show the direction of the magnetic field, we use our right-hand thumb rule. So we Using the right hand, we put the thumb in the direction of the current, and the curled fingers would give the direction of the magnetic field. Now, they would be something like this. Hopefully my diagram will look reasonably okay. Obviously we're doing this in the plane, so I'm going to have something like this. And it's because your thumb is down, your curled fingers will be going in the clockwise direction. So you're going to be having this, like this, and like that. That would be that diagram there. So that would be that. And then Satan explained whether the turns of the wire will attract or repel each other. You see, you've got something like this. So if you take this over here, you've got your current coming down there, and next to it you've got a wire also with the current going in the same direction. So let me draw another, say if you've got another wire here, and it's also got a current going in that direction. So this would also form magnetic field lines similar, like this. And there you'd use the same rule. So your thumb in the direction of the current of the right hand, curled fingers in the direction of the magnetic field. So you'd be getting something like that. And notice here, you'd be getting your magnetic field lines opposing in the middle. So these would actually cancel out in the middle. It would cancel out here. And this would actually lead to, because it's weaker, the magnetic field is weaker in the middle, over here, weaker in the middle, and to be stronger on the outside, it actually causes the wires to be forced together. So they will actually attract each other because the magnetic field lines, I'm not going to write this all down, the magnetic field lines between the conductors will cancel out, and therefore the magnetic field will cause the wires to press into each other. Using a diagram and explaining by means of a diagram would be great.